Thanks. So as Gorian mentioned earlier in this meeting, John Preskill gave a talk about quantum algorithms for solving certain quantum field theory problems to show that these problems can be done in polynomial time by quantum computers. And this talk's sort of the flip side of that coin, arguing that these problems cannot be done in polynomial time by classical computers, so that what we've expended our effort on is something that was worth spending effort on. And before I get into any details, I'd like to just give an overview of the structure of the argument. So to people with a complexity theory background, they read this, this thing, hyphen completeness, put onto the name of a complexity class, and they know right away what the structure of my talk is going to be. But many people here have not seen that before. And what it is that if you have a problem that's complete for a complexity class, any problem in that entire complexity class can be reduced, can be converted into an instance of this particular problem. So BQP is the class of problems that quantum computers can solve in polynomial time. And so the structure of our argument will be a reduction. We say we have the problem of predicting the output of some polynomial-sized quantum computation, and we want to do some massaging of that to encode the output of the quantum computation into some transition probability in a quantum field theory. And therefore, if you had a classical algorithm that could efficiently compute what those transition probabilities were, then they would be able to compute all the behaviors of quantum computers. So they would be able to solve factoring problems, for example. They could simulate Shor's algorithm and all these other quantum algorithms, which we do not believe can be simulated efficiently classically. So that's the structure of the argument to sort of argue for the difficulty of this problem. And that's the one key thing that I wanted to establish right up front. So before I go on, are there any questions about that? Okay. So first of all, do we even think that quantum field theory problems are hard? And when I say hard, I mean computationally hard here. And it does seem from experience that there's good reasons to believe this is the case in certain regimes. So we can think about what are the classical algorithms that we know for simulating quantum field theories. And I would say there's kind of two main candidates. One of them is using Feynman diagrams. And this is an algorithm which is so efficient that oftentimes you don't even need a computer to do it. You can do it with pencil and paper and just using your brain. So that's a remarkably efficient algorithm. But on the other hand, it is a perturbative method. So effectively, when you're summing these diagrams, you're sort of expanding, you're Taylor expanding transition amplitudes in powers of the strength of the coupling between particles. And if the particles are not weakly coupled, then you're not really going to get good answers by Taylor expanding to low orders. There's also a more subtle issue, which is not as widely known, which is that in most quantum field theories, these perturbative expansions are not actually convergent. They're only asymptotic expansions. And one upshot of that is that as you add more and more diagrams at higher orders, initially you're making your answers more and more precise, but beyond a certain order, as you add in more, you're actually moving away from the correct answer. So there's actually a maximum precision that's achievable by these methods. You can't go to asymptotically high precision. And the second method is lattice methods, which I think our next talk I hope will teach me more about. And in lattice methods, typically you're doing things in imaginary time. And so you're getting good information about static quantities, things like binding energies and so on. But it's generally not so good for computing dynamical quantities like scattering amplitudes. On the other hand, lattice methods can deal with strong coupling. So you can see that there's a gap left by these. If you want to go to strong coupling or high precision and you're interested in dynamical quantities, we don't have a polynomial time classical algorithm that can do that. And so people have tried very hard, and we haven't found a polynomial time algorithm for that. And so that's kind of our experience-based evidence for why we think some quantum field theory problems are hard. And so there are several different quantum field theory problems you could formulate. One of them is to ask for scattering probabilities.
Can you comment before you go on?
Yes.
Can you go back a slide?
Sure.
I've been reading preprints from places like JLab about calculating scalar sector scattering amplitudes using generalized Luther methods. So it can be done. It's just you have to sort of be an acrobat.
Yes. So there are definitely a number of specialized methods which can even fill in little pieces of the gap that I'm sort of pointing to here. And the question is, in a sense, like, will we ever find enough special techniques that we can fill in the whole landscape of different kinds of quantum field theory problems? Will someone, a clever person, tomorrow give us new algorithms that are able to cover everything? And that seems like a hard question to answer, because how could you ever find out besides trying and trying and trying? And that's the point of using these complexity theoretic methods. We can get formal evidence that no one will ever find a polynomial time algorithm that covers all the bases unless all of quantum computation can be simulated efficiently classically. So one of the problems that you might want to solve is estimating, say, scattering cross-sections. And so your input to your problem is a list of some particles and say what their momenta are. And then some time goes by, these particles come in and scatter off each other and produce some shower of outgoing particles. And you want to predict what those outgoing particles will be. What are their momenta? What types of particles are they? How many of them will there be? But this is a quantum mechanical process, so at the end you don't get a deterministic outcome. You get some probability distribution over possible outgoing particles. And so what you might demand from your quantum computer is to sample from that probability distribution. And so I think this is a relatively natural and familiar problem in particle physics. Essentially, it's what a theorist would call computing the scattering matrix. And I think experimentalists would say, well, this is at least a highly idealized sort of cartoon version of the kind of things that they measure in particle accelerators. And so as John mentioned earlier, we do have some quantum algorithms now for solving certain cases of this problem. We looked at a bosonic massive theory, which was 5/4. We have an algorithm for that, and we looked at a fermionic case. And also, as Benny Resnick mentioned, there are real experiments that people are working towards to simulate quantum field theories, not using full-blown universal fault-tolerant quantum computers, but using things that you can actually build today, such as atoms in optical lattices. So we have all these classical and quantum algorithms, but it leaves open kind of the more fundamental question of, okay, under what circumstances is this problem really hard, and in what cases can we actually solve it efficiently? So there's kind of a hand-waving argument to say that this problem is as hard as quantum computation, which is that, there are people at various labs around the world, including Chris Monroe on this very campus, who are trying to they've really built small prototype quantum computers. And as far as we know, all the physics describing those labs is contained in the standard model, which is a quantum field theory. And you could say, all right, well, therefore, simulating all dynamics that are possible in the standard model should be as hard as simulating a quantum computer, because a quantum computer is something that can exist in principle within that theory. And at a hand-waving level, that's probably an okay argument, but it leaves a lot of questions open, because a lot of times what you might want to solve is not something where the entire standard model, every single particle that exists is coming into play. You might be interested in some specialized regime where you're solving some simplified quantum field theory. And so for a given problem, what are the features that you can identify which might make it hard or easy? So some of the things which are known sort of by experience to make quantum field theory problems harder would be the presence of fermions, which can induce sign problems that make Monte Carlo methods difficult. In the case of chiral theories, there's the fermion doubling problem that's hard to deal with. If the theory is strongly coupled, then perturbative methods run into problems. Usually, the higher dimensional the space-time is, the harder the problem is. Massless particles seem to add extra difficulties, especially for the quantum algorithms. Kind of related to that is Monte Carlo methods are known to have a critical slowing down phenomenon at some quantum phase transitions. Or if you have a large number of particles, you expect on general grounds that things will be difficult. So the main result that I'll tell you today is that actually, even only having very few of these ingredients, really just the large number of particles, and none of these other things that we typically consider as things that make the problem hard, we can already show a BQP hardness result. So it's in one dimension. It only has bosons. The particles are all massive. They're weakly coupled. Already in a setting like that, we can construct a problem which is as hard to solve as simulating a quantum computer. And that's kind of the main punchline of this talk. Okay, so before I get into that, I think maybe about half the people here are specialists in quantum field theory and half are not. So I'll give a little bit of overview of the aspects of quantum field theory which are important to the rest of the arguments that I will present. So first of all, what are we thinking about with a quantum field theory? So start by thinking about a classical field theory. The classical state of that system is just the field. So, you know, a classical field is described by its value at every point in space. Here's the field of an isolated charge. You know, we can draw a picture of what the field configuration is. So the state of a quantum field will be a superposition over a corresponding classical configuration. So we could think of some kind of wave functional. For each functional form that the field could have, that corresponds to a quantum state, and we have an amplitude for that. And this is not necessarily the way we usually think about quantum fields, but in the present context, it's kind of a useful way of thinking about it. And you might ask, well, what does this measure really here? And that's kind of a subtlety which maybe we won't get into too much. So that's describing it in terms of fields. What about in terms of particles? Well, we can kind of think of particles as being a language that we can use to describe the state of the field. So a good example of that is if you have a non-interacting field theory, you could think of, say, for example, this field, which is the displacement of, say, a violin string. And we have the quantum version of that field theory. And if you've ever done certain math or physics classes, you know that you can describe the violin string in terms of these normal modes, which each behave like independent harmonic oscillators. So in a quantum context, we know that when you quantize a harmonic oscillator, it has energy levels which are evenly spaced. You just say, okay, the energy is n plus 1/2 h bar omega. And what we interpret that integer as in a quantum field theory context is the number of particles that are occupying that mode. So basically, these shorter wavelengths are corresponding to higher momenta, and we can say, okay, well, there's one particle with this momentum and 5 particles with that momentum, and so on, and that's a way of describing the quantum state of the field in terms of particles. So the specific example that we're going to look at is a quantum field theory called phi-4 theory. And one way to think of it, which I think will be maybe appealing to computer science types, is as a limit of a sequence of lattice theories. So you could think of the physical degrees of freedom living on the vertices of, say, some square lattice, for example. And these degrees of freedom are just like the displacements of this violin string. So you see this, you could have the displacement field being phi and the canonically conjugate variable, which is kind of like a momentum, being pi. They're commutators proportional to the identity, just like the x and p operators in quantum mechanics. And you have a pair of such operators associated with every site. You write down some Hamiltonian on on this lattice, and you can take a limit as the spacing goes to 0 to get a continuum limit. And the funny thing about this is that these parameters here, lambda naught and m naught, have to be tuned in a special way as a function of that lattice spacing to get this limit to first of all exist, and secondly not be just a free theory. Okay, so that's kind of my 3 or 4 slide description of the relevant parts of quantum field theory, sort of aimed at computer scientists. And now let me get to kind of the meat of the talk, which are what are the problems that you might want to solve, and what can make them hard. And so here's 3 examples of commonly solved problems in quantum field theory. One is what I already mentioned, computing scattering amplitudes. This is a very, very physical kind of question that's pretty directly related to what you might measure in an experiment. Another kind of quantity, which is maybe a little more abstract, is correlation functions. So you could take this quantum state, which represents the vacuum, put some observables in here, and calculate the expectation value of those observables, say the field at a pair of space-time points, for example. And that's a well-defined quantity that you might want to compute. And a third one, and which people commonly do, and a third one is the partition function, where now you again are sandwiching some operator between vacuum states, but this operator is really a time evolution operator. So you have, say, the Hamiltonian of your theory plus some source term in here. So this j of x is some quantity that you can have varying throughout space-time, and you add j of x, phi of x into your Hamiltonian, and you ask, given that we've kind of perturbed our system according to this source, and we start in vacuum, what's the amplitude to remain in vacuum at the end? That's the partition function. And so it's sort of, I think, obvious why people would want to compute this, but why do people want to compute these? So one reason is that these quantities can be kind of interconverted. So here's the partition function, and if you take derivatives, take functional derivatives with respect to j at certain points, you can see this is exponential of this coefficient j of x times this variable phi of x. So if you differentiate, phi of x comes down. And so by taking functional derivatives of the partition function, you can get correlation functions. So partition functions can yield correlation functions. And similarly, once you have correlation functions, you can get scattering amplitudes essentially by taking a Fourier transform. So here's some correlation function right here. We're Fourier transforming it. There's some extra fact, and this is equal to, with some extra factors out front, a corresponding scattering amplitude. This is called the Lsd formula. So correlation functions yield scattering amplitudes. And so you can see that the partition function is kind of like this master key that gives you everything else. From the partition function, you can take functional derivatives and get correlation functions. And from the correlation functions, you can take Fourier transforms, essentially, and get scattering amplitudes. And a second reason that you might want to compute the partition function is that it directly answers a kind of physically meaningful question, which is, we start with vacuum, we apply some external field, and what happens? What's the amplitude that we remain in the vacuum state at the end of that? So it's kind of like asking a question about an antenna. You have some perturbation you make in the background space by applying some field, which in this case is kind of periodically varying, sort of sinusoidally varying in space, and also in this case kind of sinusoidally varying in time. And then what's the probability that particles are produced by this? It's not a perfect example because in this case we're producing photons, which are massless. In the cases that we'll be thinking about will be massive particles, but it's I think a fairly reasonable analogy to think about what are we kind of calculating here. And so what we're going to show is that for a sufficiently general choice of this external field, this driving function j as a function of space-time, it becomes the case that computing this, this partition function, this vacuum-to-vacuum scattering amplitude, is as hard as simulating a quantum computer. And so the way it works is we have a reduction. We start with some kind of arbitrary quantum circuit, and we want to encode the all zeros to all zero bit string amplitude into the vacuum-to-vacuum amplitude of this quantum field theory process. And it's well known that all zeros to all zeros amplitude can encode any quantum computation. And so, in these reductions, there's a lot of information here specifying this whole circuit. You need some place to kind of encode that in your problem instance. And in this case, our choice of circuit is going to be encoded in our choice of this driving field, this source term J of x and t. So this is going to be some complicated function of space-time. And okay, so then how do we actually start to analyze that? So we'll do so by taking a non-relativistic limit. So suppose we have this kind of Hamiltonian, h of J2, which is our standard phi-4 theory Hamiltonian, plus a slightly different kind of source term. This is a source term with phi squared instead of phi. But it turns out that if you choose that as the source that you apply, then when you kind of take the low energy limit and end up with a fixed number of particles, what you see is we get Schrodinger's equation, where we have our usual kinetic term for the kinetic energy of each particle, plus we have a potential that they're all moving in, which is exactly proportional to J. So this is the case where J2 is constant, well, it could be constant or varying in time. And now we have a potential term acting on those particles. So what do we use that potential term for? Well, the first thing we can do is we can make a bunch of double wells. And this will all be just in one spatial dimension. And so now we can start to encode qubits by having particles occupy one or the other of these wells in each pair. So for example, we could take the logical 0 of the qubit to be the particle sitting in the ground state of this well, and the logical 1 to be the particle sitting in the ground state of this well. And now these are not actually eigenstates of our quantum system. There's some tunneling matrix element between these things, but we can arrange that to be exponentially small, so we can think of these as being essentially static states, that if we put something in the logical 0 or 1 state, it basically just stays there. And so now, once we have a way of encoding our qubits, the next thing we need is some way of simulating quantum gates on them, some way of applying unitary transformations to manipulate the states of these qubits. So first, let's think about single qubit gates. We just have some qubit sitting in some linear combination of 0 and 1, and we want to perform some 2x2 unitary operation on it, which we can think of as like a rotation of the Bloch sphere. So if we want to do like a sigma z type rotation on our qubit, it's pretty easy to think of how one might do this. So we start with, here's the 0 well and here's the 1 well, and maybe we slowly vary the wells as time goes forwards. We momentarily lower, say, the well that represents a 1, and momentarily raise the energy of the well that represents a 0. And so the 1 and the 0 will accumulate different phases because of that in the time dynamics. And then we bring our wells back to how they were, and in this way we can do a rotation e to the I sigma z theta for whatever theta we want, which we determine by how deeply we vary these wells or how long we leave them in this configuration. Similarly, a sigma x rotation, you can kind of guess how this could be done. You start with your particle. It might be sitting in the left. It might be sitting in the right. We've said that our tunneling matrix we made extremely small, so they pretty much just sit there. But we could momentarily lower this barrier to allow the particle to have some probability of tunneling across. And this rotates the 1 state to the 0 state and vice versa. And it exactly implements a sigma x rotation. And so between these two, we have rotations about x and z. By standard Euler angle formulas, we can do an arbitrary rotation of the Bloch sphere now. So that just leaves 2-qubit gates. So there's a theorem which I've heard sometimes called Berlinski's theorem, which says that if you have arbitrary single-qubit gates and you have any single entangling 2-qubit gate, then that's a universal for quantum computation. So our task now is to figure out some way of doing any 2-qubit gate that's entangling. Doesn't matter which one. So how are we going to do that? So once we're talking about entangling gates, we're talking about interacting the particles. So now we have to think about how do the particles interact. And remember I wrote the non-relativistic Hamiltonian looks like particles sitting in a potential plus an order lambda correction, which comes from the lambda 5/4 term in the original field theory. Now we actually care about what this order lambda correction is, because that's what is going to cause these particles to interact. So if you expand this out up to second order, this is what the correction looks like. And you can see it looks like an interaction between particles. So here we have like a delta function contact interaction, which is repulsive, I guess. And here we have an attractive term, which is more long range. It looks like essentially like kind of a Yukawa type potential, because these are massive particles. So we're going to have to use this somehow to implement our 2-qubit gates. So what's the most obvious idea for how one might attempt this? So the idea that seems most obvious to us is, okay, now think about on this line we have a double well, and then we have the neighboring double well, and these represent 2 qubits. So if the particle's here, the left qubit's a 0. If a particle's here, the left qubit's a 1. If a particle's here, the right qubit's a 0. If a particle's here, the right qubit's a 1. So we have 2 particles in these 4 wells. And so we say, okay, well, time is running up as usual on my slides, and so we take these wells, we momentarily take these middle 2, the 1 well of the left qubit and the 0 well of the right qubit, and momentarily move them closer together so that this interaction term induced by the lambda 5/4 will become non-negligible. And so what that means is, you know, all these other states where, say, we're occupying this well and this one, that would be this case, nothing much happens. But if we're occupying 1 and 0, then there's some energy which is going to induce a phase. So the 1-0 state accumulates a phase, and all the other states, nothing really happens, at least to a good approximation. And so this would be the gate that we make, and that is an entangling gate, and so that would satisfy the conditions of this theorem. But this does not actually work, unfortunately. And the reason is, when you momentarily bring these middle 2 wells together, you can have leakage out of the space that we're thinking of as encoding our valid qubit states. So for example, suppose we start with the left qubit is in the logical 0 state, the right qubit is in the logical 1 state. We've now squeezed these 2 wells closer together. This particle might be able to tunnel over here. Now this double well has 2 particles in it. What does that represent for this qubit? I don't know. And this one doesn't have any. What does that represent? So we've gotten outside of our coding subspace. And so at first we tried to escape from this problem by tuning parameters very carefully to try to find some regime in which, in 5/4 theory, where the tunneling between these wells is negligible, but the interaction, this induced by the lambda term, is non-negligible. But it turns out there's just no such regime. That doesn't work. So we had to do something else. And what we did was actually suggested to us by Jake Taylor, as I recall. And basically the message is, well, don't be so uptight. Just be a little bit more zen about it. Just think about this entire space in which the particles can move. This is some higher dimensional space. Maybe you could achieve universality there, and as a special case of that, you could get block diagonal unitaries, where on the 4-dimensional coding space that represent this valid 0 and 1, 1, 0, and all these different qubit states, we get the particular unitary we want. And in this other block, well, we get something else which we don't care about. So what dimension is this space? Well, it's a six-dimensional space. You could say, well, if we have 4 particles and we can put them anywhere, you might say, well, that's 10 different states you can have. But actually, 4 of those states we're protected against transferring into, because if you have 2 particles both occupying the same well, that's a very different energy, because then the interactions between them become very strong. And so if we do things slowly enough, we can use adiabatic, we can do things adiabatically, and the energy gap protects us from escaping into those states. So it's really only the states where we have 4 wells, and each well is occupied by one of these 2 particles, so the total number of states is 4 choose 2, which is 6. And we've shown in this 6-dimensional space some sequence of moves by which we can get something like this, a block diagonal unitary which does whatever we want, which does what we want on the coding space and does some other garbage on the other space which we're not occupying. So at intermediate times we're moving through this bigger space, but at the end we start and end in the coding space. Yeah? Maybe. I mean, I think that if you go to other quantum field theories, in many cases this problem can become easier. For example, if you had 2 different species of particles, one of which is your qubits that are sitting in the wells, and one of which is like a much lighter or even massless particle, which is just mediating the interactions between these things, then you don't really run into the same problem. That's something more like more analogous to QED, where you have the light photons mediating the interactions and the heavy electrons that are kind of just sitting there. And in a situation like that, then I think things do become much easier. But we kind of wanted to focus on massive 5/4 for 2 reasons. One, we just really wanted to push as hard as we could on like the simplest possible quantum field theory, which is still BQP-hard. And secondly, we wanted to match our algorithms. So we can say, on the one hand, we have a quantum algorithm which solved this problem in polynomial time. Now, on the other hand, we have this hardness result for the same quantum field theory that essentially shows that classical computers cannot do so. Okay, so now that's the essence of how we simulate our circuit in this quantum field theory process. We've got we can simulate some arbitrary quantum circuit acting on these encoded qubits. And you note that we want this to be a fully unitary process. We want to think of it as being something like the partition function or like some scattering dynamics. There's no measurements in there. So we're not doing active error correction. So in kind of this fictitious model of computing, we need if we have, say, G gates that we're simulating, we need each gate to be implemented with precision order 1 over G. So we need these gates to be polynomially precise. We can achieve that using some quantitative adiabatic theorems, which kind of tell us how much error we get as we sort of slow down the implementation of these gates slower and slower. So that's kind of how we achieve this error scaling. So the errors at the end add up to some epsilon, which is fixed and not growing with the number of gates. So that's a lot of the story, but it's not the whole thing, because recall what we really wanted was, we wanted to show hardness not of some weird problem where we start with a weird initial state, namely a bunch of particles sitting already in a bunch of double wells. We wanted to show the hardness of a more natural standard problem, which quantum field theorists commonly desire to solve and sometimes do solve, which is computing a vacuum-to-vacuum scattering amplitude, in other words, a partition function. So we need to add another ingredient, which is how do we create the particles at the beginning, and how do we destroy them at the end. And so if we were to run this circuit, and it really takes all zeros to all zeros, and we do our destruction dynamics at the end, and indeed the particles are sitting where we think they will really be destroyed. And if they're really sitting somewhere else, they will not be destroyed. And so whether the quantum circuit went all zeros to all zeros determines whether the particles go from vacuum to vacuum. So how do we do that? Well, we go back to this sort of antenna notion. And just as in a real antenna, we can sort of apply a oscillatory source term to create particles. And its sort of wavelength of oscillation in space is selecting out some momentum, and its frequency of oscillation in time is selecting out some mass. And so we can tune those so that we are on resonance to create a single particle in a well. So that's the idea. Basically, it ends up looking like a Rabi oscillation kind of scenario, if people are familiar with that. Now, just using kind of the first idea that comes to your mind, in this case also leads to a difficulty, which is, recall, we're not imagining a scenario where we have any measurements. We're not imagining a scenario where we have active error correction. Everything's just unitary. And so if we're preparing n qubits at the beginning, we need to make sure that the error induced each time is at most order 1 over n, so that the total error preparing this entire state is some constant error epsilon. And so if you try to achieve this using standard Rabi oscillation, where you're driving with a fixed monochromatic kind of driving frequency, then to achieve error order 1 over n, we need to tune the driving frequency to be equal to the physical mass of the particle to within error plus or minus order 1 over n. And so that means we need to know what the physical mass of the particles is to that precision, which is not so easy in a quantum field theory. This mass is not the same thing as the parameter m0 that you put into your bare Hamiltonian. And secondly, we also need to know this certain matrix element to precision order 1 over n, and that's not easy either. So how are we going to solve this problem? Can we compute these things efficiently to sufficiently high precision? Well, it turns out instead of solving this problem, we will avoid this problem. And this also is an idea which was suggested to us. In this case, it was suggested to us by Mark Rudner, who mentioned to me a method that is very well known and widely used amongst experimentalists, which is called adiabatic rapid passage. So instead of just driving your system with some fixed frequency, you sort of sweep slowly through a range of frequencies. And you can show that if you sweep slowly enough, and if this range of frequencies includes the resonant frequency in it somewhere, it doesn't have to be right in the middle, then you can drive these transitions from no particle to one particle with arbitrarily high precision. The errors converge to 0, and you can really show this quantitatively just by driving more and more weakly and more slowly sweeping through the frequencies without having to know the matrix element and the mass more and more precision. Those precisions you just need to have at some fixed level. So this was what allowed us to escape from this difficulty, and so we have to thank the experimentalists for having these great tricks that we can borrow. Okay, so in conclusion, the main point is that already a surprisingly simple problem in quantum field theory can be BQP-hard. Anything a quantum computer can do can be encoded in this transition amplitude, so you really don't expect to ever find a quantum algorithm efficient classical algorithm that can compute that. Otherwise, if we do, then we won't need to build quantum computers. We can just, use our classical computers to simulate this quantum field theory problem and, find the factors of gigantic numbers or whatever you want. And the interesting thing is, it's already a pretty simple quantum field theory that allows us to achieve this. It's one-dimensional. It only has bosons. There are only massive particles. It's weakly coupled. But the one kind of funny feature about it is that we're allowing ourselves this space-time varying source term. That's where we encode our problem instance. You need somewhere to encode your problem instance, all this large amount of information that specifies the circuit that you're trying to simulate. So an interesting open question, I think, is suppose you really want to maintain translational invariance or even Lorentz invariance, then what do you do? So you could imagine instead encoding your problem instance in a complicated initial state instead of a complicated source term, maybe that would allow you an alternative way of showing a different kind of BQP completeness result. I think that would be an interesting thing to do. And of course, lastly, this sort of result here kind of, bolsters the case that this quantum algorithm, which we made earlier, which John told you about, is doing something that is really a win for quantum computers, something where quantum computers can succeed and classical computers fail. So I'll end with that, and thank you for your attention.